So the last topic of this section 1.5 is going to be looking at limits as x goes to plus or minus infinity. So let's take a look at evaluating numerically the limits of e to the x as x goes to negative infinity. So we're just going to plug in some values of numbers here. So what I want us to observe is that these are x's. We're starting off at subbing in negative 10, and then we're subbing in negative 30, and then we're subbing in negative 500. So these are values of x that are going to negative infinity. All right, so if I sub in negative 10, that's going to give me e to the negative 10th. Well, e to the negative 10th would be 1 over e to the positive 10th. Now remember, e is like 2.7-ish. So think about 1 over like 3 to the 10th, right? So if you put this into your calculator, if you wanted to see what this was as a decimal, this one comes out to be approximately 0.000045. All right, so now suppose I did e to the negative 30th. Well, that's going to be 1 over e now to the positive 30th. And then e to the negative 500th would be 1 over e to the positive 500th. So what we're looking at here is essentially as these as we look at the values of these denominators, so as these denominators get larger and larger and larger, the value of the entire fraction, so 1 over these numbers that are getting bigger and bigger and bigger, these numbers are getting smaller and smaller and smaller. If you were to sub into your calculator 1 over e to the 500th, it would probably just come out and say 0 because it's such a very, very small 0.000000 type of a number that these numbers that we start to see then, but the whole idea is looking at, when we're looking for our limits, we're trying to figure out them. The whole idea is what are the y's approaching. And in this case, those y's are getting closer and closer and closer to 0. So when we look at this limit, looking at it numerically, the limit as x is going to negative infinity of this e to the x function, this is going to 0. Now, graphically, we can start to take a look at some examples, and this is something you might have touched on like in a college algebra or pre-calc class, but you might have just had a discussion about it that more was referring to it as end behavior. So on this first example, as a matter of fact, these two graphs that you see right here in the middle, these are from my college algebra class. They're from my college algebra notes. So the idea is looking at what's happening as x goes to negative infinity. So in a situation like that, we're talking about as we are traveling off, going in as the x's are going further and further to the left. So as x goes to negative infinity, we're traveling along further and further to the left on the function though, of course. And so in this situation, we would see that, okay, those y's just seem to be increasing. They're just getting bigger and bigger and bigger. So it looks like the y's are going then to infinity. And then analogously here, as I travel along further and further to the right on my function, so as my x's are going to infinity, my y's look like they're just decreasing without bounds. So we would say those are going to negative infinity. Now, on the second graph, as my x's go off to negative infinity, so as I travel further and further along to the left on my function, because there is this horizontal asymptote, it looks as if these y's are getting closer and closer to 2. And same thing happening here as I'm traveling further and further off to the right as x is going to infinity, these y values are getting infinitesimally closer to 2. So let's look at the same type of question here. We're just going to throw on the limit notation, but we're really talking about kind of this end behavior of these graphs. So number one, the limit as x goes to infinity. So as I am traveling further and further off to the right, so as the x's go to infinity, it is looking like I have a horizontal asymptotic behavior, even though I don't have the dashed line drawn in. I would say it looks like this is leveling out at approaching 3 as I travel further and further off to the left. So as the x's are going to negative infinity, again, it kind of looks like these are leveling off at potentially a horizontal asymptote at -3, even though I didn't actually draw that asymptote in. All right, next two here. So as x is going to negative infinity, so as I'm traveling further and further off to the left, well, this one doesn't really seem to be leveling out. It feels like it's almost getting somewhat linear, but even if it's linear, even if it's approaching like a line shape, that's still decreasing without bound. So on this one, we would just say that it doesn't look like this is approaching any limiting value. It looks like it's just decreasing without bound, so going to negative infinity. And then if I look at, again, traveling further and further off to the right, so as x is going to infinity, doesn't look like this is leveling off. It looks like this is increasing. Looks like it's almost becoming somewhat linear in its shape. Not exactly, but it looks like it's kind of maybe approaching like somewhat of a linear growth. But even so, that is continuing to increase without bound. So this is going to infinity. So when you look at these above examples, the two we just did, and even the two up above that didn't have the limit notation, but we're talking about the same concepts, we can see that when x is going to infinity or negative infinity, in order for the limit to exist, there needs to be a horizontal asymptote, some sort of limiting value that will be graphically what we would see with a horizontal asymptote. So in order for this limit as x would go to either infinity or negative infinity, when will it exist? Well, it looks like that's going to exist when there's a horizontal asymptote. Well, that's useful because we might know some things about horizontal asymptotes. All right, so let's continue here and get into the meat of how we're going to evaluate these, not necessarily numerically, not necessarily graphically, but what I'm going to call analytically, kind of justifying our results, proving them, if you will, without going to a graph and without going to table of values. So here's, and there's several approaches that you can take, but here's kind of one way that we can approach proving these. So what we're going to do is we are going to divide the numerator and the denominator through by the highest power of x that's in, it's supposed to be just an n there, by the highest power of x that's in the denominator. So this will really end up to being an equivalent of multiplying by a version of 1, and I'll show that with some work. So we are going to divide through by the highest power of x that we see in the denominator, and we'll do that in both the numerator and denominator. And then we're going to use kind of the fact that the one we looked at with our numerical example, this pattern that we saw, which basically says that if you have the limit as x approaches either infinity or negative infinity of a real number, a constant, over x to a positive power, as that denominator gets bigger and bigger and bigger, so as these denominators grow and get larger and larger and larger, the value of the fraction, the value of that whole term, will go to 0. So for example, so just a couple of little mini examples of this little fact, because this is an important fact in and of itself. So if I was looking at the limit as x goes to infinity of a constant, let's say -2, over x to the positive 1/2. And of course that is the same thing as the square root of x. But as x gets bigger and bigger and bigger, the square root of x gets bigger and bigger and bigger. And so as I have a constant divided by a denominator that's getting larger and larger and larger, the value of that fraction, the value of that expression, is going to 0. As denominators grow without bound, the values of the fraction go to 0. So those are the kinds of things that we're looking at here. So let's just do that one little mini example. So that's the type of thing we're talking about. So that's going to be a fact. That's an important fact just in and of itself, is this fact right here. So this fact is pretty important here. So I would say, maybe kind of highlight that a little bit more in your notes. That's an important fact just in and of itself. That's an important one. All right, so as we keep that in mind, so limit as x goes to infinity of a constant over x to a positive power is going to go to 0. And same thing if you're going to negative infinity. So those facts. Now, if we have a pure rational function, so when we talk about rational functions, we're talking about polynomials divided by polynomials. The answers we get should correspond to, what did we just end with, this observation about horizontal asymptotes. So we just said back here that a limit as x goes to plus or minus infinity is going to exist if there's a horizontal asymptote, and it's going to then approach that horizontal asymptote. So let's recall our rules about horizontal asymptotes. So there are 3 different scenarios that you look at when you're talking about your rules for horizontal asymptotes. So our first one says if the degree of your numerator is greater than the degree of your denominator, then there is no horizontal asymptote. I like to think of that as like x squared over 1. The parabola doesn't have a horizontal asymptote, or x over 1. A line doesn't have a horizontal asymptote. So if the degree of your numerator is less than the degree of your denominator, so the most basic example here would be like the function 1 over x. That has a horizontal asymptote at y equals 0. So that has your horizontal asymptote at y equals 0. And then in the last case, the degrees, if they're equal, if the degree of your numerator is equal to the degree of your denominator, and there's no kind of really nice way to express this, so you just sort of have to write this out, but then you're going to have a horizontal asymptote at y equals, and it's the ratio of the leading coefficients. So the coefficients in front of the terms of highest degree. So if we do our above work correctly, then if it's a rational function, then the answer we get should coincide with these rules here, meaning if the degree of the numerator is greater than the degree of the denominator, there will be no limiting value, meaning our answer will end up either just being infinity or negative infinity. If those degrees are, degree of numerator, is less than degree of denominator, then our limit should be 0. And if the degrees are equal, we should end up back at the ratio of the lead coefficients. So that is very useful. All right, let's take a look at some examples here. So our first one, suppose we're looking at our limit as x goes to infinity of -2x to the 4th minus 3x, all divided by 4x squared minus 1. So if, I'm going to prove this one using this first major technique, and then I'll just see if it coincides with what we know about horizontal asymptotes. So what I said to start, and first of all, keep in mind, this technique is for limits as x goes to plus or minus infinity, right? You can't, let me start by saying, you can't plug in infinity. It's not a number. So there is no direct substitution. You cannot do it. And in fact, a lot of the things that you might think might be true about infinities aren't. Like you can't add and subtract infinities in a meaningful way. Infinity minus infinity, for example, is another indeterminate form. So a lot of the things that you might think you can do with infinities, you can't. So this is what we're going to do. So we are going to start off and we're going to do it sort of the long proof way. So I said you're going to divide through the numerator and the denominator, each term, by the highest power of x that is in the denominator. So I am focusing on the highest power of x that is in my denominator here is 2. And that's why I'm dividing through by x squared. So we're following this first bullet. Divide numerator and denominator by highest power of x that's in the denominator. Okay, so this is multiplying by a version of 1. So what's going to happen is because I am multiplying this entire thing then by 1 over x squared, and so the entire numerator and denominator, this is going to amount to, and I am okay if you started it with how I'm going to write out this second step. This is the same thing as saying, okay, so I'm going to have negative 2x to the 4th minus 3x, and I am going to be dividing each of those through by x squared. And then that whole thing is divided by, and I have 4x squared minus 1. And again, I am dividing each term by my x squared. So the first step shows why it's legal, right? I'm multiplying by a version of 1. The second step might be like the more practical place to start. Now what we're going to do is we're going to reduce. So we are going to reduce in this case. And so if I have x to the 4th divided by x squared, I can reduce, and this is just going to give me an x squared. The x divided by x squared, I'm just going to have x. The x squared over x squared. So what am I now going to have? I'm going to have my limit as x goes to infinity of negative 2x squared minus 3 over x, careful on that, and then all over 4 minus 1 over x squared. Now, every place that there's an x, I have to think about what's happening as x is going to infinity. And in each of the terms where I have a constant over x to a positive power, we know from what I have highlighted in yellow, those will go to 0. So based on that work, here's what I know. As x goes to infinity, oops, I meant to just highlight that. As x goes to infinity, constants divided by x's to positive powers. So those values of those fractions, those go to 0. 1 over x squared is going to go to 0. Now, negative 2x squared, that is not negative 2 over x squared. So negative 2x squared, that's not going to go to 0. You know, infinity times infinity, infinity squared, is going to just continue to increase without bound. So x squared, as x goes to infinity, x squared is going to continue to get bigger and bigger and bigger and bigger. So what am I going to, so those are all the places where I have x's. So I'm going to have this first term looks like negative 2 times, something that is approaching, that's getting bigger and bigger and bigger, something that is going to infinity. And then I have minus something going to 0, divided by 4 minus something going to 0. Well, 2 times something going to infinity is going to mean that this first term, a negative number times something going to positive infinity, is going to be going to negative infinity. And so this numerator is going to be going to negative infinity. The denominator here is going to be going to 4. I mean, I guess you can think about saying, divided by 4. But then a number going to negative infinity divided by 4 is still going to be a number that's going to negative infinity. So in this case, this limit, well, it's not really a limit, is it? It's decreasing without bound. So it is answered as negative infinity. Now, what I want you to observe is from the very beginning, if you thought about your rational functions and their horizontal asymptotes, in the very beginning, we could have noted that the degree of your numerator, highest power of x, was 4, and that was bigger than the degree of your denominator, which was 2. And so that meant that there was no horizontal asymptote, which of course means that there is no limits. And so no limits makes sense with the fact that this limit actually went to negative infinity. So there was no limiting value to it. Going through those steps was useful because I was able to determine in the end if it actually was decreasing without bound or if it was increasing without bound. And I found out it was actually decreasing without bound. But it does coincide with and make sense with the rules I think about with my horizontal asymptotes. All right, let's look at another example here. So number 2, suppose we had the limit as x goes to negative infinity of 4x minus 3 divided by the square root of x squared plus x. All right, well, this one's a little different. It's not just a polynomial divided by a polynomial, so I can't really talk about like the degree of that denominator. But I can talk about the highest power of x that I see in that denominator. And the highest power of x that I see in that denominator is an x squared. But this time it's an x squared that is inside of this square root. So if I'm thinking to myself, well, I'd like to do something analogous to what I did last time, which was I was dividing everything through by the highest power of x I saw in the denominator. I like that idea, but the problem is it's not just dividing through by x squared, because that x squared is underneath a radical. And if my goal is eventually to divide like this term by x squared, it's under the radical, so I have to multiply. The only way I can multiply into a square root is if I multiply by another square root. So I need to think about that. That highest power of x is x squared under a radical. Now, I mean, yes, I want to keep this equivalent, but I don't love the look of that. Like, that doesn't look so good, especially when in the numerator I have a polynomial. So what I want to think about here is this square root of 1 over x squared. Well, that's just the square root of 1 divided by the square root of x squared. That's not too exciting. And of course, square root of 1 is 1. Okay. Now, the square root of x squared, technically, by definition, is the absolute value of x. It's not just x. And the reason is, if you recall back in a class when maybe you first learned about radicals, if x has the potential to take on either positive or negative values, like in here, we don't have any restrictions on x, so x could be a positive or a negative number. So notice, yeah, the square root of x squared becomes, square root of 3 squared becomes 3, because the square root of 3 squared is the square root of 9, and the square root of 9 is 3. But guess what? The square root of negative 3 squared, it's also the square root of 9, and that's also 3. So I don't get back to, so this did not come out, this second one did not just come out to be, oh, the square root cancels, for lack of a better phrase, with the square, and I just get negative 3. That isn't what happened, right? So this is just a little review for you of why, technically, by definition, you get back to the positive form of that x. So technically, by definition, the definition of the square root of x squared is technically the absolute value of x. And we know that technically the absolute value of x, we've talked about this, it has a piecewise function and definition, and it is equal to x if you're talking about values of x greater than or equal to 0. And if the x itself is negative, then we take the opposite of that negative in order to get back to our positive result. So if x is less than 0, then you end up with negative x. Well, here's what we have to look at. This is a limit as x is going to negative infinity. X is going to negative infinity. So these are x's that are going to be less than 0. And so that's going to mean we're going to need to use the negative x definition. So after all of that, what I now know is that the square root of 1 over x squared is going to equal either 1 over x or 1 over negative x. In this case, it's 1 over negative x because I'm looking at the limits as x goes to negative infinity. And that's why we ended up with the negative x on that. So believe it or not, what I have in red in these brackets, that is a version of 1. It may not feel like it. It doesn't look as neat as the last one did, but it is exactly that. So now we are going to kind of do the same thing that we did before. We're going to have to multiply, this in to both terms here. All right, so what do we have? So we have our limit as x goes to negative infinity. We have the 4x minus 3. Each of those terms now being divided by a negative x. That whole quantity divided by, and I'm multiplying 2 square roots, so I can multiply what's underneath of 2 square roots. So that means I can now divide each of these terms under the square root by their little 1 over x squareds. And then, of course, you're just going to be doing a little bit of reducing here. So you're going to reduce, your x over x. Here, x squared over x squared is going to be 1. You can reduce one of those in that second term under the radical. And so what do we have? We now have our limit as x goes to infinity. Looks like in the first term I have negative 4. In the second term I have plus 3 over x, all divided by, in my denominator, I have 1, plus in my second term, I have 1 over x. So again, as x goes to infinity, I dropped my negative, as x goes to negative infinity, any of these terms that are constants over x's to positive powers, those terms go to 0 as x goes to either infinity or negative infinity. And in this case, that's the only 2 locations I have of x's. So it looks like I will have a negative 4 plus something going to 0 divided by the square root of 1 plus something going to 0. So negative 4 over the square root of 1 is just going to be negative 4. So that one was a little bit trickier, but built off of the same kind of initial concept there. But it was not purely what we would call a rational function, because it was not just a polynomial divided by a polynomial. All right, let's end with one last example here. And this one will be, again, maybe just a little different than the others. Suppose we have the limit as x goes to negative infinity of 4 cosine of 2x over x squared plus 1. Well, this one sort of defies everything, right? It's definitely not a polynomial over polynomial. It's not just a straight rational function. And it doesn't even look like something like number 2, that I can adapt my process for rational functions to fit this. I mean, what happens to cosine as it goes to negative infinity? I mean, it just oscillates, right, between 1 and negative 1, and then times 4 in the numerator, so it's going between 4 and negative 4. So what we're going to do with something like this is we're going to get an opportunity to use squeeze theorem again. So if you kind of heard what I was just saying, it's like cosine is going in between negative 1 and 1. Oh, I have some bounds on that. So that's what we're going to do here. So we're going to start off and we're going to say, so it's certainly true, we've talked about this before, that cosine of or sine of a function is always bound between negative 1 and 1. Sine and cosine, no matter what's on the inside, the outputs are always in between negative 1 and 1. Okay, so now what we want to do is we want to think about, in our next step here, we're just going to multiply kind of all sides through here by 4. So on our next step here, we just want to multiply everything through by 4. And so keep in mind what my goal is. Like, why am I doing that? I'm trying to get my function whose limit I'm trying to investigate. I'm trying to get it bound in between some other functions that maybe I can evaluate. So there's the numerator of the function I'm interested in. So now, in order to create the function that I want, let's divide through by the x squared plus 1. And that's going to create the function that I want. So remember, x squared and then plus 1 would be positive. If you are dividing through by a negative, you have to reverse inequalities, but we're not here. So I'm dividing every part of this compound inequality. I'm dividing that through by the x squared plus 1. And so I now have the function I'm interested in bound in between two other functions. So now what we're going to do is then we're going to take our limits. So we have an inequality, we have our function bound between a couple of other functions. And now what we want to think about is taking the limit. In this case, the desired limit is the limit as x goes to negative infinity of each of these components. So the negative 4 over x squared plus 1 less than or equal to the limit as x goes to infinity of 4 cosine of 2x over x squared plus 1. That's what I'm really trying to figure out. Has to be less than or equal to the limit of 4 over x squared plus 1. All right, so these limits on the ends of this compound inequality, these we know, and I'm going to allow us here within the context of this bigger problem to apply our rules about horizontal asymptotes. So in both of these cases, these are limits going to negative infinity of rational functions. So in both of these cases, actually, hold on just a second. I already have a times 4 that I wrote up above with an asterisk. So let me, instead, I don't want to confuse that. Let's put a star here. Okay, so off to the side, here's what I want you to note about both of those. So in both of those situations, the degree of the numerator is a constant, and so that's 0. And that is less than the degree of the denominators, which are x squared as your highest power. And when the degree of your numerator is less than the degree of your denominator, that means there is a horizontal asymptote at y equals 0. And that means that is our limit as x goes to negative infinity. So we opened this video really recognizing that limits as x goes to infinity or negative infinity will exist where there are horizontal asymptotes. So that's a good justification for that one. So off to the side, we were able to apply that kind of line of thinking. And so I'm going to have 0 for both of those limits. So I now have 0 is less than or equal to the limit as x goes to negative infinity of 4 cosine of 2x over x squared plus 1 is less than or equal to 0. Well, there we go. We have now our bounds to be able to apply our squeeze theorem. So by the squeeze theorem, that means that this limit, if it's both greater than or equal to 0 and less than or equal to 0, that implies by squeeze theorem that it has to equal 0. So that's how we would prove that one. All right, so that's the last example in the notes.